in this series of videos, we're going to tune a resist parameter set. We're going to start with our empirical data. This is our measured data that we have compiled in a spreadsheet here. So on the stepper, somebody went out and printed 4 different patterns, lines and spaces, CD of 45, pitch 230, that's case 0, CD of 45, pitch 300, CD of 45, pitch 600, CD of 115, pitch of 230. So at a numerical aperture of 1.35, dipole Y polarized illumination, sigma outer, sigma inner, and at 193, a defocus range of minus 100 to plus 100, so this is our FEM, our focus exposure matrix, and doses of 10, 11, 12, 13, and 14. So that's our setup. Our raw data, suppose somehow after metrology you got the raw data, it comes back in this form here, defocus, dose, case, and the CD, or the measured, and then you've got this data here. And here it's been sorted by case on this sheet, and then here we've got bosons. Okay, so this is our empirical data. The idea is that we're going to try and find resist parameters that make the simulated results closely match this. Okay, so now the first thing we need to do is make a HyperLith setup that matches our experiment. A HyperLith setup that generates these cases. So let's refresh our minds here. We've got NA 1.35, CD of 45, pitch 230, 300, 600, and 230. So let's do that first. So first we're going to set up a chrome-on glass Kirchhoff mask, a line space pattern. We're going to parameterize the pitch, and the first one is 230. The CD is 45. And we're going to give the CD values. So the next pitch was 300, 600, and 230, 45, 45, and 115. Okay, so this matches our experiment that was run. But because these values are non-uniformly increasing, we're going to insert a variable and call it case, and this will be a pilot variable, and now everything will go off of case. Okay, one thing I forgot to mention was that there are biases on each of these cases. So this case has a bias of -2, +2, +6, and -21. So we can just add those here, add another variable, call it bias, and lock it. -2, +2, +6, -21. Let's verify that those are correct. -2, +2, +6, -21. Okay, and then we need to use that here in the bias. So that makes our pattern, our set of lines on the mask, match our experiment. Now we have to set up our imaging system. We'll choose DUV dipole, 1.35 NA. We'll increase the samples on the sampling of the source and its water immersion. And we're going to use, for the resist model, we're going to tune the PRM, ARF panoramic resist model. Okay, without it has no, we're not going to use the film stack, and we're going to tune this resist. First, let's just see if this is making any sense here. Oh, we need to set up our focus exposure matrix. Let's go look back here. We've got -100 to +100 in steps of 25 for defocus, and then we've got 10, 11, 12, 13, and 14. For so 12 is our nominal dose, and we need to figure out what percent variation gets us 10, 11, 12, 13, and 14. So let's go back to our spreadsheet, and we'll just say equals 2 divided by 12. That's 16.6667%. So we go 16.67%. So that'll give us a dose of 10, 11, 12, 13, and 14. Again, this has to match what was done experimentally. And this would give us minus 100 to plus 100 in 4 steps on each axis. That would be 25 nanometers. Okay, let's save this. Refresh our live view. These are all locked. So when we simulate this, this should give us 4 bosons. Alright, so let's go plot our bosons. Okay, so there's our 4 bosons. That's our simulated data. Okay, so again, we need to make these bosons match. So far, we haven't done any tuning. All we have done is set up our HLN file, our HyperLith setup, to match the experimental conditions. And we've got it generating a boson. In the next video, what we'll do is we will allow these resist parameter values to be variables, and the tuner will run the tuner, and the tuner will adjust these variable values to make the simulations match.